In this first problem, we're shown a portion of a backhoe that's digging into the earth. We're told the hydraulic cylinder AB on the backhoe produces a 4,500 pound compressive force, and we'd like to determine the forces in members BC and BD. Take a moment to pause the video and resume playing when you're ready to see a solution. Like many of these problems, there's a lot competing for our attention in this figure. We're actually shown only a portion of the backhoe, and so the arm extends beyond the figure that we're immediately given. The backhoe itself is represented in yellow, and each of these linkages, the hydraulic cylinder and the links BD and BC, are shown in gray, and that's drawing our attention to the intersection of those three pieces. It doesn't do us much good to try to draw a free body diagram of the backhoe as a whole because the shovel is interacting with the earth and we don't know what forces exactly are exerted there. And there are internal forces between the portion of the backhoe that we can see and what extends beyond the figure. So really, we're again looking at an intersection of elements. The most natural place for us to focus then is on this joint B where these three pieces come together. Each of these links is pin connected to other pieces. So there's a pin connection at B, C, D, and A all represent pin connections, and that's going to be important to us because it's going to mean that each of these members carries a load along its geometry. So each piece is either going to be in compression or in tension, and the force is going to be aligned with the geometry. We know the force carried by AB, it's 4,500 pounds in compression. A couple of choices that are available now are first in terms of the coordinate system, how should we represent this problem? And then how should we determine whether the members BD or BC are in tension or compression? Can we see anything about that in the problem? Now, one of the things that's given in the problem statement is that the angle BC makes with the line of action of AB is given by 20 degrees. So I'm just going to extend this line of action a little bit and then make a note that on either side of AB here, this angle, this would subtend 180 degrees on this side, and of course it would subtend 180 degrees on the other side. Since we're given that BC makes a 20-degree angle with that line of action, and BD makes a 70-degree angle on the other side, what we can see is that this angle between BD and BC must be 90 degrees. So 20 plus 90 plus 70 is also 180. On that basis, then, it's most natural to establish a coordinate system that's actually aligned with BC and BD. That's its own mutually orthogonal system. I'm going to call the axis that goes through BD X, and I'll call this positive axis Y. So in an XY system, I'm going to have this is going to be aligned with BC, and this is going to be aligned with BD. And then the force that's provided by the compressive member, the hydraulic cylinder AB, is going to be pushing into that joint. So I'm going to call this as the compression in AB, and that's going to make this 70-degree angle with the axis that goes through member BD. Now what I can see from that is that the force that's provided by BC is going to have to react the vertical component of the compression in AB, and member BD is going to have to react the horizontal component. That tells me that the member BC is going to be in compression. Again, I can verify this after the fact, but I'm going to represent this as the compression in BC. And then I ought to have a tensile component in BD to react the horizontal component from the hydraulic cylinder CAB. So because I've taken some time to think about what my appropriate coordinate system is and what the signs of the loads are in these different members, that's going to make the rest of the problem now very simple. So if I write sum of the forces in X equals 0, I simply have TBD minus CAB cosine 70 equals 0. And in the y direction, I'm going to have CBC minus CAB sine 70 equals 0. So now I don't even have to solve simultaneous equations in this case. I can just write the results down directly. So I have TBD is equal to CAB cosine 70, that's 4,500 pounds, cosine 70, and that number turns out to be equal to 1,539 pounds. And CBC, compression in BC, is 4,500 pounds times the sine of 70, and that's equal to 4,229 pounds. Now, a couple of things here. First, if you chose a different orthogonal coordinate system, you should get exactly the same numbers. You didn't have to do it the way that I did it here. And the fact that these numbers both turned out to be positive indicates that I represented them correctly in my free body diagram. So in fact, BC is in compression and BD is in tension. As a second example, we have this pair of problems, 328 and 329, where we are supporting a delicate stone beam with a combination of pulleys, and we're told that if the only significant mass is that of the beam itself, it has an 800 kilogram mass, we want to determine the forces in cables ACB and CDE. So the first thing to notice here is we know exactly what force is carried above pulley D by the cable segment that comes off that shackle. Formally, we could get it by drawing a free body diagram around this entire thing. If we do this, then the only forces that we have to worry about are the force F and then the weight of this beam, and the weight, of course, is not the mass, it's equal to m times g, and if we put in 800 kilograms for the mass and 9.81 meters per second squared for the gravitational acceleration, this turns out to be 78.48 newtons. You'll notice that nothing about the pulleys is included in this because everything about the pulleys and their cable segments are interior to this enveloping surface. So the equilibrium equation based on the free body diagram of this whole assembly is just F minus W equals 0, or the force F up here is 78.48 newtons. Okay, so we'll use that result. I'm going to erase this now. And just write that F is equal to 78.48 newtons. And so now we're looking for the tensions that are carried by these two cables, CDE and ACB. And we might just note that because of the symmetry of the problem, the tension carried by cable segment FEG will be the same as that by ACB. So this looks pretty complicated. What can we do with this? So again, there are a lot of things competing for our attention in a problem like this, and we're going to be drawn to places where different system components are coming together. And the two natural places for us to look are first at this pulley at D, where we have the shackle and the cable coming off the top. We know the tension in that, it's 78.48 newtons. We're cutting through the cable segment twice on either side. And also we can take a look at free body diagrams for either ACB or FEG. Now, we said in a previous problem that when we have an arrangement like this where we've got a shackle that is connected to a cable, and we've got a cable draped over the pulley on either side of it like this, then we can say something right away about the geometry of the problem. because if we're treating the pulleys as frictionless, the cables all have the same uniform tension. And so I might just make a note here that this is all one cable segment here, as is this, all one cable segment. And then separately, I could say this is also all one cable segment here. Okay, so what can I say about this? Well, we said last time that if we considered a coordinate system for one of these shackles where we had a tangent normal system and the tangent was coincident with the line of action of the cable attached to the shackle, then the fact that we had the same tension on either side of the cable ACB meant that the line of action that I've shown here as a dashed line has to bisect that angle. So the angle made by this segment ACB is 60 degrees. That means that these two angles have to both be 30 degrees. And so that in turn means that the angle here is also 30 degrees. Now, having identified that, finding the tensions in these two cable segments becomes very straightforward because you'll remember having established that the cable that comes off the shackle bisects that angle. We don't really need an equilibrium equation normal to that line of action because equilibrium is automatically satisfied there. So if I simply call the direction aligned with these cable segments, if I call this the tangent direction, I'll call it the tangent direction in both cases. One for CDE at the top there, and then separately when we get down to this lower cable segment we're examining the pulley at C, I'll further call this a tangent direction. So that there are two unit vectors in the tangent direction there, but the one at the top goes with pulley D and the one at the bottom goes with pulley C. So now let's take a look very quickly then at what we would get for our equilibrium equations in the tangent direction. So for pulley D, remember our free body diagram now is going to look like this. We have F here, and we've got the tensions in CDE to be the same on either side. And this angle is, again, 30 degrees on either side. Equilibrium in the normal direction is automatically satisfied, so if I look at sum of the forces in the tangent direction equal to 0, that's simply going to give me F minus 2 times the tension in CDE cosine 30 equals 0. And so that's going to give me that the tension in CDE is F over 2 cosine 30 degrees. I know that F is 7848 newtons, and so if I put that in for F and divide by 2 cosine 30, I get 4531 newtons for the tension in CDE. Now, if I do the same thing for the pulley at C, and I'm going to have now essentially exactly the same free body diagram for the pulley at C that I do for the pulley at D. Instead of looking at it in the coordinate system or in the geometry of the original figure, I'll just reorient pulley C so that the cable coming off the shackle at C is now vertically oriented. This will again be the tangent direction. So now this is TCDE, again bisecting the cable ACB. Again, this angle is 30 degrees on either side. And I'm going to have the same equation in the tangent direction now. It's just that I'm going to have TACB is going to end up being the tension in CDE over 2 cosine 30 degrees. And having just found that the tension in CDE is 4531 newtons, I can divide that by 2 cosine 30, and I end up with a tension in ACB of 2616 newtons. As our last example, we have a variation on the previous problem where now the assembly is a little more complicated still. We've got still these 3 sets of pulleys. We've got a symmetric system, but now we've got a bar, CE, that is linking pulleys C and E. That's going to complicate things a little bit. But take a moment now and pause this video and try this problem yourself, and then resume playing when you're ready to see a solution. Okay, once again, I could begin by drawing a free body diagram around this entire assembly, and I would end up with F being equal to the weight of the system, and that's just determined by the mass of the beam. Again, that turns out to be 7848 newtons. And so now I'm explicitly given the angle that's made by CDE, and so I'm going to know that the angle here is 60 degrees. And so I could draw a free body diagram of pulley D based on, for instance, this enveloping surface. And the only difference between this and the previous problem is now the angle that this makes with the vertical is 60 degrees on either side. And so my equation in the tangent direction, where I again align the tangent with the force coming off the shackle, is going to give me that F minus 2 CDE cosine 60 in this case is equal to 0. So that's going to give me the tension in CDE is equal to F over 2 cosine 60, but the cosine of 60 degrees is a half, and so this is just going to be F, and the tension in CDE is going to be equal to 7848 newtons. Now, before we proceed, we might just notice that this particular configuration has resulted in a substantially larger tension in cable CDE than was present in the previous problem, and so maybe this isn't that great an idea, but nonetheless we'll proceed and take a look at what the tension is in cable ACB. Okay, so now once again our attention should be drawn to these pulleys because they represent the intersection of many different members. And one of the things you'll notice in this case is that we don't have the same angle between C and D and AC or CB. And so we no longer have this issue of the cable bisecting the angle below it because we've got another member which is now changing the equilibrium of the problem. So we'll once again follow our procedures and draw a free body diagram for pulley C. Here we have the pulley, we have cable CDE coming through the center of this pulley, and that's making an angle of 30 degrees with the horizontal. We're cutting through the cable ACB twice, once on this side and once on this side, and these are making two different angles. One angle is on this side, it's 30 degrees with the vertical, and it's 45 degrees with the vertical on this side. The tension in ACB, both sides here, And now we're not quite done because we're also cutting through this bar, CE, and so we're going to represent that as exerting a force on the pulley as well, where we cut through that. It may not be obvious to you, but because of the way this is configured, we're going to need this to be in compression, so I'm going to represent that as being in compression, pushing into the joint, so this is the compression in CE. And now that's everything that's acting in the figure, so we'll go ahead and draw, or we'll go ahead and write our equilibrium equations based on that free body diagram. I'll use an XY coordinate system. In the X direction, we have the tension in ACB times the sine of 45 degrees. And again, make a note here that I've got one angle defined off the horizontal and two off the vertical, so my use of sines and cosines depends on how those angles are defined. I have TACB sine 45 degrees, and then in the minus x direction, I've got TACB sine of 30 degrees. I've got plus TCDE now cosine 30 degrees, since that angle is defined off the horizontal, and then minus the compression in CE equals 0. And in the y direction, I have TCDE sine of 30 degrees, and then the two sides of ACB make a negative contribution in the vertical direction, so I'm going to have minus TACB cosine 45 and minus TACB cosine 30 equals 0. I can actually solve the second problem first, because I can write that TACB is going to be equal to the tension in CDE times the ratio of the sine of 30 degrees to the sum of cosine 45 plus cosine of 30. And since I've previously found the tension in CDE as being equal to the force F of 7848 newtons, when I plug these numbers in, this turns out to be 2494 newtons. It isn't specifically requested in the problem statement, but I can go back now and find the compression in member CE, and that value is TACB times the difference between sine 45 and sine 30 plus the tension in CDE cosine 30. When we plug those numbers in, it gives us a compression in CE that's equal to 7313 newtons. Again, the fact that these numbers turned out to be positive tells me that I represented them correctly in the free body diagram. We might again note that the compression in member CE is awfully high, so this particular configuration relative to the first one has resulted in a modest tension in the cable ACB in both cases, but it has resulted in a substantially higher tension in CDE and a higher compression in CE in the second case relative to the first case. So it remains to be seen as whether or not this second configuration is really a better way of supporting that beam.